Ever wonder how they build those massive chemical plants? Believe it or not, it all starts with some seriously complex math.
It's a huge undertaking, right? So where do engineers even begin the design process?
Well, without these equations of state, designing a chemical plant is pretty much impossible. It all boils down to one crucial number: specific volume. This single value dictates the size and therefore the cost. Okay, but how do you find this number, especially for gases under really extreme pressure? This is where an equation of state comes in. It's basically a formula that connects pressure, temperature, and volume. You've probably heard of the ideal gas law. It's simple, but it's not accurate enough for high-pressure reality. For those high-pressure situations, we need much more powerful models to get the job done. And yeah, as you can see, with models like SRK and Peng-Robinson, the math gets complicated fast. Solving these by hand is pretty much impossible, so we need a much better way to do it. And that's where Aspen HYSYS comes in. It's the professional simulation tool that does the heavy lifting for us. All right, let's solve a real problem here. We're going to find the volume of N-butane using the SRK equation. So, first, we just plug in the basics: our component, the fluid package, and the exact conditions. Next, we just tell HYSYS exactly what we need to calculate. Here, it's the molar volume. And just like that, the answer pops up instantly. All that complex math, done in a second. And there it is, 2.058. This is the exact number we need to design the plant's equipment. But what happens if things change? Like, what if the temperature in the plant isn't always the same? For that, HYSYS has a feature called case studies to analyze exactly these kinds of scenarios. And look at this plot. It shows exactly how the volume increases as temperature goes up. But does the choice of the equation model actually matter? Let's run a quick comparison and find out. And yep, if we switch the model to Peng-Robinson, we get a slightly different answer for the molar volume. So why does this matter? Because it's how engineers make real-world decisions about size, cost, and optimization. So it leaves you with a big question. When a tiny difference can mean millions, which equation would you trust?